طيب بسم الله الرحمن الرحيم. So the first chapter of the course and the book is basically talking about solar radiation in general. Now we are going to have a little bit of a focus. The focus here is related to what of that solar radiation is available to us on the surface of the Earth, and what kind of data that will be available, and how to use this data, because this is all some sort of a preparation to the applications. For example, the target, and I've just again and again like to remind you that the target is at the end to see how much is the potential of using a solar collector, for example, to grab some heat or to generate some electricity. So this is at the end is what we are looking for some applications. In order to do that, an introduction to solar radiation has been given in general. And here we are going to talk about the available solar radiation on the Earth. Next chapter is going to be like some sort of a quick revision to some of the basic principles that we have studied in heat transfer and so on. So as if we are going like step by step, laying the foundation of the information needed for the applications that we are looking for. So what we'll be talking about today is the available solar radiation, the instruments that are used for measuring the solar radiation, the data available for the solar radiation, and being able to calculate and predict values of solar radiation flux, be it irradiation or irradiance. It depends on the kind of information that are available and how we can process this information to get some useful values. We do not base the predictions or calculations of the solar radiation attenuation. The word attenuation you're going to hear a lot, which is reduction of the solar radiation as it comes through the atmosphere. We have seen that whatever is reaching to the tip or the outside of the atmosphere is basically the solar flux or the solar constant. However, when it reaches inside the atmosphere, this value is reduced. It is reduced because of scattering, because of absorption by some of the molecules, for example, water vapor molecules or carbon dioxide. And the issue of being reflected back again, this is because of these particles as well. Clouds are scattering, yet absorbing, as well as reflecting some of the solar energy falling. So for prediction of the solar radiation that's supposed to be in the future, we use the past measurements. So we should have a history of measurements that would be enough for us to predict what is going to be the solar radiation in future based on the previous data for whatever seasons that we have and location. The data of the solar radiation are available in several forms. The most detailed information available are beam and diffuse solar radiation on horizontal surface given on an hourly basis. And sometimes you can find information on inclined surfaces, but for shorter time intervals. The daily information and are available often. Hourly information can be estimated from the daily ones, which means that you would not always have a detailed information of hourly thermal radiation or radiation values that are falling. The monthly solar radiation can be used. It can be integrated, for example, to obtain how much would be the average monthly. And in some applications, we need this information. Actually, you are going to see in some information or some cases where we need to get, for example, you need to put a solar collector for water heating in your house. And you need the solar collector to be placed, and you put it in a certain tilt angle, which is equal to the latitude of your city. And you keep it there, you don't change it day by day. So you want to keep it at a constant value. And you need to see how much energy is it going to be falling on it for the whole year. So you are going to do it month by month. So the monthly data would be the kind of data that you would be looking for. The process information are not linear, which means that we don't expect the changes of the radiation to be linear either on hour or on a monthly basis. Accordingly, if the average are going to be used, then we should take care that some errors in the process can occur due to the nonlinearities of these values which are collected. The data can be reduced to manageable forms by using statistical methods. And this is basically the way that you'll find it's being used for predicting the solar radiation. What we see here is some sort of primary direction radiation fluxes on the surface or near the surface, near the ground, which are important for connection with solar thermal processes. We need to predict how much is it so that we can determine for this quantity or this rate of heat transfer that you need to get, how much collectors are needed, or what's the size of the collector, what's the total Q that should be like radiated to the collectors by the sun so that we can expect how much energy we can get. What we see here basically is the difference again between beam radiation, which is basically this, it's the radiation falling here, whereas the diffuse solar radiation, it's the radiation coming from different scattered radiation beams. The beam here is coming directly from the sun. These are coming from reflections from particles from the cloud. And what we are looking for as a total radiation is the summation. So when you're talking about total radiation falling on the ground, this is a summation of beam and diffuse solar radiation. The straight lines here of the arrows indicate that it's a short wavelength radiation. And by short wavelength radiation, we do mean that it is radiation which is originated from the sun. The short wavelength radiation is associated with high temperature source, whereas whatever is coming from the ground or close to the ground temperature, we call it a long wavelength radiation, which is associated with lower temperature, definitely compared with the sun temperature. And it is expressed here in this kind of corrugated lines. So straight lines represent short wavelength radiation. These corrugated or wavy sort of lines are representing the long wavelength radiation. And the long wavelength radiation definitely are supposed to be sort of diffuse radiation. The solar or short wavelength radiation is the radiation coming from the sun in the wavelength between 0.3 up to 3 micrometer. This terminology is used throughout the book. Solar radiation would mean both a combination of beam and diffuse radiation. Are we able to distinguish between them? The answer is going to be yes, even with some instrumentations that will provide us with this kind of reading. So it's going to segregate or differentiate between beam radiation and diffuse radiation, and devices that are measuring both or the total of solar radiation which is falling. This is again a reminder of what is beam and what is diffuse radiation. You have seen this slide in the previous chapter, but this is just a reminder that we're looking for beam radiation. It means that radiation which is falling directly into a surface, which is like this, or a person, whereas the diffuse radiation is the one that has been scattered by molecules that are suspended in the air. It can be by the molecules, it can be by clouds, like what you see here. The window is receiving beam radiation, and it is receiving diffuse radiation coming from another source that reflected the beam radiation, which is the clouds or sand particles or whatever particles that are suspended in the air. And there is reflected radiation, which is coming from the ground.
Doctor?
Yes.
So if there is a cloud, will we get electricity from the solar?
Will we get what?
If there is a cloud that prevents the sunlight, will we get electricity from solar cells?
Yeah, we are going to get, but we are going to get a reduced value. And your question, is it specifically for the solar cell or in general?
In general, I mean, not
Yeah,
specifically.
in general, yes, because whenever you have clouds, it means that it is a source of diffuse radiation. Because clouds are receiving energy or beam radiation from the sun, and they diffuse this radiation in all directions. And part of it will be falling on any surface around. So,
And
yeah,
and
you
doctor,
expect that.
we took in the other course that the maximum efficiency we took, I think, up to 24%.
Yes, this is
Why is it this low?
the efficiency here is the efficiency of the outcomes or the outlets of a PV panel. A photovoltaic panel, when you are talking the efficiency here is the ratio between the amount of energy that you get in the form of electrical energy divided by the incident energy falling into the solar panel, which means that if the solar panel is receiving 1000 watt per meter square, for example, then what you get is going to be 200 or 240. If it is receiving 400 only because there's a cloud which is covering partially part of the sky and it is receiving less radiation, then what you are getting is something between 80 and 90 watts. So the efficiency here is related to the material which is being used and the way that it is converting the falling radiation energy into useful energy. What we are talking about here is the falling radiation energy. So the instruments and the issue of the efficiency is something which is yet to come. This is in one hand. On the other hand, basically the kind of PV panels rely mostly on beam radiation. However, when we are talking about heating process, and for heating, what we are looking for is both diffuse and beam radiation. And accordingly, although it might be cloudy and the PV panels would receive less energy directly coming from the sun, but the solar collectors that are using heat are receiving higher values because they have or they receive both diffuse and direct or beam radiation. Did I answer your question?
Yes, thank you, doctor.
Okay.
Doctor,
Yes.
can you go back? Yeah. For the diffuse, radiation, it is what I understand. It is some kind of reflection between the particles that are some suspended in the atmosphere.
Yes.
Since it is a reflection, why do we distinguish this kind of deflection by saying it is diffusion? Is there something special about it?
No, the point is the clouds or the particles are not preventing the surfaces from receiving radiation. And if you are talking about the total amount of solar radiation that we receive, it's a combination of both. Part of it is beam radiation, which is direct exposure to the sun, and the beams have not been meeting any surfaces or particles on the way, so it's coming directly to us. But this is not all what we are receiving. What we are receiving is more than that. We are receiving a combination of radiation, and this radiation is beam plus what is being reflected from other sources, including the particles that are diffusing those radiation out. So if you need to talk about how much energy that we are receiving, we are not receiving only beam radiation, we are receiving a combination. And this is, we need to see what are this combination and how it can be measured. Because at the end, what you are looking for is you have a surface on the ground and you need to see how much is the total thermal radiation falling on that surface. It's not all beam radiation. This is why you are interested in the diffuse radiation. I hope I answered your question.
Yes, thanks.
Long-wave radiation is the radiation originating from sources at temperatures which are lower than temperature of the sun. It's in the ordinary ambient, something like the bodies which are around us. and normally they are at wavelengths greater than 3 micrometer. The long wavelength radiation emitted by the atmosphere, by a collector or other any surface at ordinary temperature, this radiation is, if it is coming from the ground, if it's coming from the sources around us, we call it terrestrial. This is in contrast with, if you remember in our previous chapter, we were talking about the radiation which is falling from the sun up to the surface of the atmosphere outside. We call it extraterrestrial. So now there's the extraterrestrial, which is basically coming from the atmosphere without being attenuated, because it's basically moving in space where there's no atmosphere at all, compared to what we get around us, which is reflected from surfaces around us, or this is what we call the terrestrial radiation. We will be, in our next chapter, it's supposed to be a sort of revision to the heat transfer part, and I'll try to bring some examples which relates something that you have studied in heat transfer, that relates the amount of thermal radiation that you can calculate based on different values of the wavelength. Maybe you can put it in the form of an example or so. Coming to the instruments that are being used for measuring radiation. This is the first one we see. It's basically done for measuring beam radiation, and it is called pyrheliometer. It's an instrument which use a parallel detector. They call it a collimated detector for measuring solar radiation from the sun and from a small portion of the sky. Basically, as you see here, the long tubes that it has, it is allowing us to, or allowing the device or the sensors to receive direct energy, which is DNI, as you can see it here. So it's basically measured, or it's basically made for measuring beam radiation. The way that these collectors or these instruments are working, whether it is this one or the next ones, the idea basically is depending on the ideas which are similar to the thermocouples. You must have heard about the thermocouples. You must have seen them in your course of, or the lab, which is associated with the heat transfer course, because we rely on the thermocouples a lot. What happens in the thermocouples, you have two dissimilar materials. One of them is at higher temperature, the other one is at lower temperature, and the difference of temperature generates what is called the electromotive force, and electricity is being generated. The amount of electromotive force which is generated is proportional to the temperature difference between them. And this is how, and this then is calibrated, and the millivolts as electromotive force is being converted or actually calibrated to indicate the temperature differences. Very much the same is the idea that we have here, the idea of having sort of using or utilizing the Seebeck effect. The Seebeck effect is basically the idea or the main principle behind the use of the thermocouples. The same things here. We have a couple of junction. One of them is facing the solar energy to receive the energy. The other one is not, and it's connected to the metallic part of the device so that it measures the temperature, or actually it's at the ambient value. So you have two dissimilar junctions at two different temperatures, and this is how the measurement starts, whether it is for the pyrheliometer or for the pyranometer, which is a device that we use a lot in order to calculate the total hemispherical radiation. So this one measures beam plus diffuse radiation. In most of the devices that, or in most of the cases where we try to measure solar radiation in our surfaces, we use this value, because we need, what we are interested in is the total amount of radiation which is falling. Actually, we use this, or what we call a solarimeter, which is basically right here. So this you can find here. We are using this a lot in our instrumentations. If you happen to visit the university and look at the places at the outside of building 26, you are going to find this, something like this, which is connected to a readout, and the readout measures the watt per meter square directly, which is the kind of total radiation falling into the surface. This one You can find it also in maybe in one of the devices that we have here, so that you can use it to measure how much is the total thermal radiation falling into a surface. And I'm putting here like a links down there. The links are actually coming from the company which is producing this device, and it's talking about basically the basic idea of operation, either for the pyrheliometer, which is this one, or the pyranometer, which is that one. And it's talking about basically the idea behind which this is operating. And it's also talking about why do we have two domes here. We have two glass domes for this one. And there are two types of pyranometers, the one with a single dome, ones with two domes. This is basically to reduce the reflected infrared radiation, which is coming from long wave length sources around it, so that it only measures what's coming from the sun. And the dome is originally placed here so that you can reduce the effect of the surroundings. You don't need heat transfer by the wind, for example, by convection to be affecting the reading, so that a glass or a glass dome is being placed. A couple of domes, as I mentioned, for attenuation or reduction, trying to eliminate the radiation which is coming from any other source other than the solar energy. What we see here, this is a way that we can measure the diffuse radiation alone without beam radiation. What does it do? It makes a shading on the direct radiation falling into those domes, those glass domes. So it is basically heated by the diffuse radiation, which is coming from the clouds, from the particles suspended on the earth, and so on. So in a trial to measure each part of them separately, so beam radiation, we have the pyrheliometer, the total radiation is the pyranometer, and the shaded pyranometer is the one that reads or basically gives readings which are related to the diffuse radiation. Again, what we are interested in as engineers is the total amount of radiation. The issue of having segregating them is this is just for documentation, data, maybe used by the people in physics if they are interested in this kind of values. The solarimeter is working as the same principle as the pyranometer. As you can see it here, it is reflecting the total amount of radiation which is falling. And there is the actinometer, which is very, you can say that it's another title for the pyrheliometer to be used. Then these are some people who talked about these ideas of operation or the basic principles of operation of these devices in general. And there's a part here that we're doing as some sort of a self-reading. I'm leaving it for you to go through, which is just getting or reading in details more about these devices. I put a link there, which is the link that explains how this instrument is operating. And you can find definitely if you search through the internet for other sources, you can find more and more information about this. I just put this as some sort of a guide where you can get this information. You can also read in the book, it's given some sort of a more of detailed information about the utilization or about each one of them, and whenever it needs like a correction factor or not, like the shaded parameter, this one needs a correction factor as the values may change with months or with latitude. The same thing again. This is a link for you to read more about the pyranometer in addition to what you have there in your chapter. As if I'm going to be talking about the section, so section 2.3 is the one which is talking about the pyranometer, and 2.2 is the pyrheliometer. So that's in sections 2.2 and 2.3 of the book. So read it there, and if you needed some sort of updates or the way the instruments would be looking like, then you have the links down there. it's not only that we like or we want to measure the flux of the solar radiation, but we need to measure also the duration. Like practically speaking, how much hours for the sun above a certain threshold. By threshold, I mean a certain value of radiation flux. Say some references would take it as 150 watt per meter square, for example. So how long or what's the number of hours where the thermal radiations are going to be greater than this value? This is what is being called bright sunshine. The time in which the solar disk is visible for using the long-term average of solar radiation. Two instruments are being widely used. One of them is the what we call the Campbell-Stokes sunshine recorder, where basically it has a solid glass. You can see a glass here with 10 centimeter diameter, and it produces an image of the sun opposite to a surface here. So as if it's collating the amount of energy coming from the sun all into a certain point here. Using a special type of papers, this is going to leave like a burning trace on that paper. So a strip of standard treated paper, a special type of paper, is mounted around an appropriate part of the sphere, and the solar image burns a mark on the paper whenever the beam radiation is above a critical level. So at a certain level, as I mentioned, it can be 150. It depends on what is the value that you're looking for. And then this burnt value changes as the sun changes location in the sky. And at the end, the length of the burned portions of the paper would provide an index of the duration or the total duration of a bright sunshine. This used to be the old school, or originally it started like that. Now with the PV panels, things have changed. You don't have to get special types of papers. You don't have to get them burned so that you can see the trace of this of the duration of solar radiation above a certain value or above a certain threshold, as I mentioned. For this one, the interpretation of what constitutes a burned portion is uncertain. This is some sort of a less or qualitative kind of measurements. It does not respond to lower level, as you mentioned. It only gives the amount of sunshine above a certain value. However, a photoelectric sunshine recorder, which is basically based on the utilization of photovoltaic cells. These photovoltaic cells are basically based on selenium, which is a non-metallic element used to fabricate those cells, where basically one of them is exposed to the solar radiation, the other one is shaded, and if there's no beam radiation at all, both of them are going to indicate the same reading, but with beam radiation on one of them and the other one is covered, then you are going to measure the difference, where the critical radiation difference between both of them is going to be a measure of the duration of solar radiation over the day. Before I get into that solar radiation data, let me pass quickly through your names. I've noticed that there was, we had a latecomer today. So Abdul Hadi Abu Zaid.
Yes.
Abdullah Abu Shaya. Abdul Rahman Al-Mashhaf. يوسف المهيش.
موجود يا دكتور.
عمار الثومي.
Yes, دكتور موجود.
حسين الوحيد.
Present.
صالح البليهي.
Yes, doctor.
عبد الله الدوسري.
Yes, doctor.
عمر الجهني.
Yes, doctor.
عبد العزيز المقتوي.
Yes, doctor.
عمر الشمري.
Yes, doctor.
عبد العزيز الشهري. ريان الودعي.
Yes, doctor.
فهد الزهراني.
Yes, doctor.
عبد الرحيم بيمة. نواف الكعبي.
Yes, doctor.
أحمد خوارج.
Yes.
أحمد سندي.
Yes, doctor.
I have to consider it. You joined too late today, Ahmed, so I have to consider that. Yasser Shaitel.
Yes, doctor.
So just in case I missed them, Abdullah Abu Shaya.
Yes, present, doctor.
Oh, okay. Abdurrahman al-Mashaf. Abdul Aziz al-Shehri. Abdul Rahim Bima.
Yes.
So Abdul Rahim,
Present.
you're here? Oh, okay. What about Yasser Shaitel?
Yes, doctor.
Okay. Okay, so what we might be looking at again is the solar radiation data that can be available in several forms actually. And there are some information that we would know to understand that the kind of radiations that would be available, that we should be identifying whether these instantaneous measurements or values integrated over a period of time. And to know this, the data should be basically explained what kind of data is there, but we can see that even from looking at the units of this data. If we are talking about units that are given in watts per meter square, then basically it is, or these are values that are instantaneous. But if you integrate it over the time, it will be given in terms of joules, like joules per meter square. So that will tell whether the values are instantaneous values that are measured on the spot, or they are values that are integrated over a certain period of time. The certain period of time could be through an hour or through several hours, like days or even months. The measurements we should identify, are we reading or are we getting beam radiation, diffuse radiation, or total radiation? We should be knowing what is the surface receiving this radiation. Is it horizontal or tilted? Because we have seen in our previous chapter that we can use the horizontal radiation to estimate what would be the tilted radiation. So we should know the radiation that we are getting. What is it? Is it falling on horizontal surface or on a fixed slope? If they are averaged, and if they are averaged, then upon what period? Hourly, monthly, daily, whatever. So these are the kind of information that we should know while we are using values that could be tabulated in books or references, or you can get it from the internet as well. But you should know whether it is, again, instantaneous or over a period of time integrated, beam, diffuse, or total, horizontal, tilted, and if they are averaged, then is it like hourly, daily, or monthly? Why is that? Because you can find this combination available. So you can find data which are basically hourly, you can find data which are given as instantaneous data, you can find daily, you can find monthly, and each one of them may have its own application. The two types that are widely available are the monthly average daily total radiation on a horizontal surface and the hourly total radiation on a horizontal surface for each hour or for more extended period of time than that. The H values, which are the month averagely radiation are available, and you can find some of them in the Appendix G. Do you have the book or not?
Not yet.
I do.
Me not.
Yes.
I do have the book.
Not yet. Some of you may have it then, but if it's not yet, I think there was a practice last semester by the university sending you the books by mail. I would hope that would be the case, but anyway, I'm trying to put as much details of the chapters as possible in this presentation, so that you can have almost details of the information that are given in the books until you receive it. And if I need something from you for extra reading, like what I did for the instrumentations, I put a link on the internet where you can get the information from. So at least until you get the book, that might be soon or not very soon, but at least you have your sort of complete source of information that you would need for studying.
Thank you very much.
Most of the radiation available are basically for horizontal surfaces, and this is what you will see most. And we have known that, or we have seen from examples in chapter 1, that how you can get the tilted radiation on a certain surface by starting from the horizontal values that are being provided. Most of the instruments provide radiation records as a function of time. Actually, you may have a pyranometer, and the pyranometer could be either connected to a readout. This one is going to give you instantaneous values on the spot, how much watts per meter square. But this can, or the instrument itself can has a way for storing the data, or it can be connected to a data acquisition system so that you can start storing all the values so that you have instantaneous values over a certain period of time. And then if you wish to get averages, what you need to do is to integrate it over the hours. There are data that are available which are similar to the ones that will be shown in figure 251 by recording the potentiometers and integrated graphically. The data which are related to radiation values, you can find it in sources. I remember that there was a project that started in the 1990s here in the kingdom, and they were trying to make like what they call a Saudi Atlas, which is several versions of it is available now. But I remember at that time they were trying to collect data from different weather stations all over the kingdom. Some of these data are given in details, hourly or daily basis, and some of them we have some data and there are some days or some months where the data are missing. And they're trying to collect all this information to make like a database of information. Some of the data were for about 20 years, some were less, depending on the weather station and when the weather station was installed. But this is some of the important meteorological kind of information. And even before, there were some sort of sophisticated instrumentations that are used to be in weather stations. Now things are much easier. We can run an experiment in any location, and we can get the information that we want locally. For example, you can get a pyranometer, you can put it there, you can get thermocouples to measure the temperature, you can get some instrumentations for measuring the humidity of the location. So humidity, temperature, you can get something to measure the velocity as well for the wind speed, which means that you can do your own calculations. But this is going to be only for the period you are running your experiments. If you needed the information for extended period, then you need to go for sources. One of the stations is located within the university. It's for the RI. You can find it on the top of building 15, which is the research institute. And I do remember that sometimes we do values, we do calculation related to solar collectors, and we try to collect values of the solar radiation falling into the pyranometer. And then I would call someone that I know, for example, in the RI, and I tell them, please send me the radiation information of yesterday. Then he would send me like an Excel file that has hour by hour what was the values of basically temperature. And by temperature, I mean dry bulb and wet bulb temperature. You have all taken the course of ME439 So you know, I would assume that you know what's the difference between dry bulb and wet bulb temperature. It will give me the value of the relative humidity. It would give the value of the wind speed and radiation as well. And then it depends, is it measuring like total radiation, H, or only beam radiation, which is I. So now it depends on the instruments that you are using. Sometimes they're providing both of them. And again, most of it will be radiation on a horizontal surface because this is the origin. If you need to calculate the radiation on a tilted surface, that's something that you can work it out later. But at least having raw data of radiation on horizontal surface for every latitude, and each station is located at a different latitude, is something that you would need. Most of these instruments provide radiation records as a function of time. It is operating all the day, and all the values that falls, it is recorded and being saved in a file, and then you are making your measurement continuously, but you record the measurement every second or every few minutes or every half an hour or every hour. It depends on how you are setting your instrumentations to do. I do remember in some of our experiments, we used to measure actually, the devices can measure depending on the accuracy of device and the response of the device, maybe every 1/100th of a second, 0.01 seconds. But normally we don't need that. Changes are not that abrupt. So we just adjusted that it can measure by the frequency it does, but it only records the values every second or maybe every minute or every 5 minutes. It depends on what do you need in your experiments, how much changes that you are looking for. Maybe every 15 or 30 minutes. I would sometimes, when students are working on a solar energy application that we have, I ask them that take the measurements only if once after every 15 or minutes or maybe half an hour, because the changes in the radiation flux is not significant over a certain small period of time, unless there is a cloud which is passing and it affects the readings, then definitely we'll need to account for this. This is sort of a plot that shows the uncertainties in integration and in parameter response. What is being seen here is the amount of solar radiation, watt per meter square, over a day from 6, or actually it's from, I think it should be the other way around, from 6 a.m. to 6 p.m. And it is showing it on a clear, shiny day, clear sky on the top figure, and on a cloudy day in the bottom figure. And you can see the differences here. Clouds are basically affecting the solar radiation. It's not eliminating it totally, but it's affecting it, except for a few days, which would not be here in the kingdom, but they are in some places. The clouds are covering the sun the whole day, and you don't see the sun for a day or even more. That was values that you can get. You can hear, for example, say at a certain part of the day at noon, I can get how much is the radiation as watt per meter square. And here at noon, you can get the radiation per meter square. Here we are talking about something in the order of 200 watts per meter square. On the other hand, here we are talking about something in the order of 700 watt per meter square. So roughly you can estimate what's the value here. Some photographs or some graphs like this one are giving us worldwide map of radiation, and the color scheme here is showing roughly the fluxes. So that, why do we need that? Because if you need to measure the potential of solar energy in some places in the world, you can use it, you can get it using a figure like this. And there are so many of these figures that are there that will tell you how much is the solar energy. It could be, for example, some sort of an average over a year or average over months, and there's lots of figures that are providing this kind of information. Or tables like this that are providing us details of meteorological data. for example, the solar radiation here, I, which means it's solar radiation integrated. And this is an example of our hourly radiation over the hour. So this is integrated values of the radiation over an hour. It is given not only that radiation, but it's given the air temperature and the wind speed. And this is specifically in Colorado, if I'm not mistaken. Yeah, Colorado Boulder. So it's in a city in Colorado, the United States, that are providing this kind of values here. So for the 8th day of the year, and for the hours from 1 a.m. after midnight, extended to 12 noon, and then here from 1 o'clock in the afternoon up to 24 hours. So the upper portion of the glass is taken a whole day, and it is integrated. How integrated? When say that it is hour number 1, or let's take an example for hour 8, which is 8 o'clock in the morning. The value of 17 is not instantaneous at 8, but this is an integrated radiation from 7:30 to 8:30. And then when I'm talking about 2 o'clock in the afternoon, 14, the 1252 is not exactly at 2 o'clock, but this is an integrated solar energy between 1:30 and 2:30, and it is given in the middle, which is exactly 2 o'clock. So that's the way it is given here, and the temperatures are being provided as well as the wind speed. Wind speed is important because it tells you the potential of utilization of wind energy. I mean, is it worth to put a windmill at this location or not? That's something, again, which is important. And you'll find that there are some places, for example, it's not only places, but times. Look at the values here in day number 8 are not high, but in the 9th day, the values of the wind speed are higher. That's the 10th day are higher and higher. So that will give you an example. For example, what's the potential, not only of this, but the potential even of solar energy. Look at day number 10. It was a sunny day, so it was given us values of the radiation flux as much higher compared to the values that are being given in the previous 2 days. So this is a piece of information that would be extended, that would be available for every day for several years. Year to year, the variations are not usually abrupt, except for sometimes you can find that. You can have, for example, you can have, like in the news, that we are being exposed to a hot day that we have not witnessed for the last 30 years. How do they know? It's because they have data that are stored for 30 years, and they do the comparisons to see whether we are in the same annual trend for these values of temperature, of the solar radiation, or wind speed, or we are going off record by having exceptionally higher or lower values. So that's for measurements or calculations of the dynamic behavior of solar energy equipment and processes. For long-term processes that you need more and more detail, and the more details that you have here, the better that you would have, because you can make use of this data to calculate daily average, monthly average, or even the annual potential for using solar energy. If you are buying a solar collector, you are not buying it to use it on the 10th of January only, but you are buying it to use it over the year and for several years. So you should make sure when you are doing your calculations, for example, I need hot water from my house, then what is the type of solar collector I should buy, and how many solar collectors I should buy. That's mainly dependent on what's the weather conditions that you have around you, and based on that, you can make your selection. You may have a day which is exceptionally cold, so that your solar collectors are not providing enough heat, but that's an exception. Like when you buy an air conditioner, and the air conditioner is good as long as the temperature around us here for Dhahran is 45 degrees centigrade, which is design temperature for the air conditions. What if you have a few hours in the whole year where the temperature is not 45, but it has gone upper to 50? Then you might not be very comfortable in your house, but that's not a very long period of time. It's something like moments that pass. If you need to make your system based on a degree, 50 degrees, then you are oversizing the unit, and you would basically be paying a lot capital cost, which is the cost of the device and installation, and you are paying higher running costs because of the cost of electricity that you are going to pay for a bigger compressor. Or you may go for the norm, which is like 45 degrees centigrade. You are going to pay less, but you may be suffering just for a few hours maybe every year or every other year or so on. So that having the data available is going to help you make your decision regarding this issue. I remember that once we had air conditions that we have been using here, and they were just being designed to give us like a nominal design temperature of the outside that should not exceed 95 Fahrenheit. And then we were suffering from discomfort for several days over the year. And then after that, they have, in the next batch of air conditioners that were bought, they have changed it to air conditioners that are dealing with a nominal temperature or a design temperature of 105 Fahrenheit, which made more sense in the way that it provided comfort for most of the year. So the same thing here. If you know the data that you have, you can make your decision of what kind of devices or instruments or equipment that you need to buy based on the values that you have. This is another representation of the atmospheric attenuation. Attenuation again means reduction. Part of the solar energy coming is being diffused by particles or by the clouds, and some ground reflection, which is about 5% of the incident energy on the ground, is being reflected to the surroundings. And that's something that I've seen some are taking it, or people are taking it into consideration. If you have to design an air conditioning system, but this is some sort of very detailed information that normally practical engineers do not do. It's basically for researchers or for coming up with a basis maybe for correlations that can be used for the estimation of the cooling load of a certain building, that there is some sort of internal heat sources like people, like equipment. There's external heat sources like heat transfer through the walls, and there is radiation through the glass, including a part of ground reflection that can be added to the amount of heat added to the building because of the reflected energy coming from the ground. Solar radiation at normal incidence, which is received on the Earth, is subjected to variations. The variations could be atmospheric scattering. We talked about that a while ago, talking about diffuse radiation, which is caused by water, by dust molecules or air molecules, or absorption by some gases that are there. Ozone can absorb a considerable part of the ultraviolet energy. Water vapor can absorb thermal radiation. CO2 absorbs thermal radiation. And this has all have been reported, and people were looking at this in details. Scattering of the radiation as it passes through the atmosphere is caused by interaction of radiation with air molecules, water vapor or water droplets, and dust. The scattering is a function of number of particles through which the radiation should pass and the size of particles that are compared to the wavelength that are actually opposing to the radiation which is falling. Absorption and scattering. Scattering, we have seen that it can be done by the dust particles suspended in the air, while absorption can be occurring by some of these gases. For example, ozone layer is absorbing the ultraviolet. Water vapor and carbon dioxide are absorbing the infrared kind of radiation. There's complete absorption of short wavelength radiation by ozone in the upper atmosphere at a wavelength below 0.29 micrometer. And that's probably why we were hearing a lot the issue of the ozone layer, or the ozone hole, which is a place in the atmosphere that is not covered, that's not filled by the ozone, and this is how the ultraviolet are escaping and reaching the atmosphere. And this is basically is not a useful kind of radiation which is falling. So the ozone absorption decreases as the wavelength increases above 0.29 micrometer until the 0.35 micrometer, where there's no absorption there. By the way, last year, due to the COVID-19 and some of the many activities that were reduced or suspended, the news came saying that the ozone layer has been full now. So it means that the ozone hole has been filled with ozone, and then it's again came back to protect the Earth from the ultraviolet radiation which is falling from the sun. Water vapor absorbed strongly in the band of the infrared part of the solar radiation, and it is strong absorption is in the range between 1 to 1.8 micrometer of wavelength. Beyond the 2.5 micrometer, the transmission of the atmosphere is very low due to the absorption by hydrogen, by water droplets and carbon dioxide. So when we are looking at the whole picture as you can see it here, the energy in the extraterrestrial spectrum at wavelength greater than 0.5 micrometer is less than 5% of the total solar spectrum. The energy received at the ground at that range, which is greater than 2.5 micrometer, is very small. The figure that you see here in front of you is indicating that based on the wavelength, the absorption is occurring by what? For example, here in the short wavelength radiation, ozone is making absorption. So the amount of solar energy is reduced, which is reaching the atmosphere or the sea level is reduced compared to the, let's see, the outer one, which is the red one, is the black body radiation falling from the sun. The solar irradiation outside the atmosphere is done by this upper black line, whereas what we are getting here is the lower line, and those green dots are the attenuation or the reduction in the solar radiation that happens due to absorption of water vapor, oxygen, and water vapor at different, you can see this is all at different values of the wavelength of water vapor. And then at longer wavelength comes the contribution of carbon dioxide. So carbon dioxide is absorbing here and here and here. You can see there is a big portion of the infrared radiation which is exposed to absorption by carbon dioxide. And you may link that if you wish, but what has been mentioned earlier, that the increase of carbon dioxide in the atmosphere results in global warming. You can see here it is absorbing substantial amount of radiation falling by the sun, and more carbon dioxide around us is going to mean more absorption. Carbon dioxide is an absorbing, or we call it a participating medium. So it absorbs the solar radiation, and the particles of carbon dioxide are getting heated. Because it is heated, it convects heat to the air, and then you can have global warming or warming in the area or the atmosphere, which is having high concentration of carbon dioxide. To summarize, the normal solar radiation incident on the ground has a spectral distribution. The spectral distribution basically is, which means that there is radiation associated with each wavelength. The X-rays and other short wavelength radiation of the solar spectrum are absorbed high in the ionosphere by nitrogen, oxygen, and other atmospheric components. Most of the ultraviolet is absorbed by the ozone layer. For wavelengths or for long wavelength radiation greater than 2.5 micrometer, a combination of low extraterrestrial radiation and strong absorption by carbon dioxide means that very little energy reaches to the ground. So the amount of radiation that we are affected really with is somewhere in between 0.29 and 2.5 micrometer that needs to be considered in the devices that we are using. This is an indication of how much the wavelength, the midpoint wavelength, and the energy band. We have seen this figure or a similar figure to that in chapter 1. Actually, this is not the same as table 131, but it's very much similar to table 132, which is found in the first chapter. And by the way, until you can get the hard copy of the book, I think the internet is having some free version of the book. It's an earlier edition, maybe third edition or so. The one that we have here in the bookstore is the fourth edition. So for a purpose of calculating the material properties and the material or the surface properties, as you have probably remembering from heat transfer, is the surface absorption, the ability of the surface to absorb energy, which is needed for solar heaters, for example, where you are painting your surface with black paint to absorb energy as much as possible, gets heated, and the heat is being transferred into a medium like water or oil, heat transfer oil, or air for heating purpose. So absorption there is important. The other component is reflection, which is basically for shiny surfaces that you don't need them to heat, but you need them to focus the energy on a neighboring surface. And some of the parabolic trough collectors or are basically of that type, so that the energy will fall into it and then it will be reflected into a tube that has a fluid inside to be heated. So this is an example of using reflection. And transmittance, basically transmission is something through the glass. So when you have something covered with glass, because you need to have the solar energy penetrating through the glass to the inside, and the glass transmissivity then has to be high. The summation of the absorptivity, reflectivity, and transmissivity is equal to 1. A black body, which is a special case, would have absorptivity closer to 1, and the reflectivity and transmissivity each is almost approaching 0. Whereas a shiny surface would have absorptivity is almost 0, but the reflectivity is greater than 90%. On the other hand, glass is going to have a transmissivity closer to 1, 0.9, 0.93, and then the absorptivity and the reflectivity are almost negligible. So now it depends on what is your target. Is your target to absorb the energy, to reflect, or to transmit? And then you make your selection of the material based on that. There are programs like SmartS that can be used to calculate the spectral energy arriving on the Earth at different atmospheric conditions. And the table that we see here is showing terrestrial spectrum, which can be used for typical distribution of terrestrial solar radiation. And the table here has been done for, definitely it has a special case, because for every location, for every condition in the atmosphere, you may have a similar table that depends on location and depends on the time at which it's being considered as well. Radiation data, the raw data, you are collecting as much as you can out of this raw data to come up with average incident radiation on surfaces. If these data are missing for a certain place, then we try to use the statistical methods to predict it, or maybe use a near place where you have some data so that you can use it for the prediction. For example, data on Khobar. Maybe Khobar does not have a station, a weather station to get the values, but we have one in Dhahran, which is nearby. So maybe you can make use of the data in Dhahran as a representation for Al-Khobar. Al-Dammam could be the same, but the conditions between us and Al-Dammam, although it's only at 20 to 25 kilometers, but sometimes it might not be exactly the same, and the kind of error here can be there. And the best thing is to have a weather station in every city, and even in between the cities, because there's potential utilization of solar energy in everywhere. So having more and more solar stations and collecting the data with high density over the whole kingdom is something of a value. But you need to make use of some sort of rationale of how many weather stations should I put, and who's going to maintain and collect the data from these weather stations. Cloud cover data is also available. but it is based on maybe some sort of estimation or monitoring over the years if the information are there. This is an example of monthly average hours per day of sunshine. How much or how many hours have the sun been shining in several locations all over the world, depending on different latitude values. In Hong Kong, in Paris, in Bombay, in Sokoto, in Nigeria, in Perth, Australia, in Wisconsin-Madison, in the United States, that are given for a certain number of months. So for the whole month between January, for the whole year between January to December, and then an annual average is being given there. Here it is providing us with small n bar, which is the monthly average daily hours of bright sunshine according to latitude and altitude. And that's why these kind of cities were selected. And I just got this information from one of the papers I was searching last night, and I found that there are data for the solar irradiation in the Kingdom of Saudi Arabia, but basically are in different places within the kingdom. And you can see it here in Afif, in Ahsan, Dawadmi, الحنكية, الجبيل, الخرج, القنفذة, العوينة, الوجه, دمام University, Daba, and you can see Hafr al-Batin, you can see Haql, you can see Kakir city, which is there, which is the recent and the most accurate. And then King Abdulaziz University, KAUST, KFUPM, and then Layla, Majma', Usfan, and so on. So in different places throughout the whole world is there. What is through the whole kingdom? It's being given there. What is given? It is the average daily total horizontal or total horizontal radiation, as you can see it here, as watt-hour per meter square. This is the red bars. The green bars are for the direct normal radiation, and the blue ones are the average daily total radiation on a horizontal surface that's been given here. And here you can say, for example, if we're looking for normal radiation, so PV panels are there. The best places to put the PV panels here, the higher values are given basically in places like Daba, like Umlush, which are basically in the north. And normally the north of the kingdom is the best place to put the PV panels. Whereas if you are looking for placing what we can say horizontal or basically the solar collector, then several places can be useful for that. Not the north, but look at Tabuk and Haql for the values of the average daily total horizontal radiation. This is a little bit lower than what you see, for example, in places like we can see here Al-Qunfuda is higher, like Wadi Dawasir, the value is high, like in Layla and Majma' it is high. And so that's some sort of a comparison between these different components of solar energy. And searching on the net or going to the Kakir, probably I mentioned that if you visit the Kakir site, you can find that there are many data. Once you just substitute there, you can just log in and have like an account for yourself. Then you can ask for data that can be emailed to you. This is a sample of empirical relation. The original, it's called the original angstrom regression equation, which is relating the monthly, average monthly daily radiation to the clear day radiation in a location, any location based on its latitude and altitude. H bar is the monthly average daily radiation on horizontal surface. H bar C is the monthly average clear sky radiation on the same location. A and B are constants for the empirical relation. N small bar is the monthly average daily hours. That's the one that we have seen. The previous table is providing that small n bar. Whereas the capital N bar is the monthly average of maximum possible daily hours of bright sunshine. So this is one of the formula that we can use for coming up with the monthly average daily radiation on a horizontal surface if we know what are the values for the clear sky. So the problem with this equation is being able to determine these values, small n bar, capital N bar, and HC, the clear sky information, and the small n bar, which is given in the table. It's not available for every city in the world. Some of them are instrumental problems, like the n over n, and some of them are related to how would you define a clear sky? Is it sky with no clouds at all over the day, or a certain small number of clouds and only for a short period of time? So this kind of uncertainty is affecting the whole formula that we have here. However, people came here and say that actually it was Page in 1964, that was several years ago, or several decades actually ago, have modified the equation that we have before, and we said instead of taking the clear sky as our reference, let's take the extraterrestrial values as the reference. And then the value of H naught has replaced the HC. So H naught here is the extraterrestrial radiation for a location which is averaged over time period in question. A and B again are constants depending on the location. The ratio H over H naught is what we call the monthly average clearness index. And we are going to use this value later in the course. So remember that H bar over H naught is what we call average clearness index. The estimation of the values of H naught can be calculated from an equation that we have taken in chapter 1, which is equation 110.3, using the day numbers, knowing which day of the year that we are in. And we have a table that also provides us this numbers. For example, July number 1, instead of counting January is 31, February is 28, March is 31, May is 31, June is 30, counting all together and then reaching for July 1. This table can give you the values at the beginning of every month. And we have seen this table, you can find it in our first presentation. Or it can be obtained from table or figure 110.1. So this table or figure is providing us with this estimation. 110.1 is basically, if you have a version of the book, then this can be found basically on, let me tell you here the page number where these figures are being given. Yes, it is basically given in page number 38, and the table is given on the second page. These both figures and the tables are given in the presentation that we have in our chapter 1. So basically, it is given us the value of H naught, extraterrestrial radiation on a horizontal surface, as a function of day of the month for the whole year and the latitude, which is given in the X direction. So based on the latitude and the day of the year, then you can determine what will be the value of H naught. So H naught, which is the value that you have here in the denominator of this part. So H naught can be calculated. A and B, there are tables that will give you A and B as a function of the latitude, and then the value of small n can also be found from the table that we had earlier. Capital N can be calculated from an equation, and we have taken an equation again in chapter 1 to calculate the value of capital N. What are we looking for here in this table? We're looking for this H. So H naught, we can get it from tables or charts. A and B are constants that you can find in tables as well. Small n, there is a table that gets this value. Capital N, there is an equation that provides us with n, and then you can get the value of H bar. It becomes the only unknown in this equation. Then we are going to have an example. Probably this example, we can keep it for next time. We can begin with that example as as of how to calculate the value of H for a certain city. The city given in the example is basically Madison. And what will be done here? We're going to look at calculating the values through this formula. We have some data available for this city. Normally we do this correlation if there are no data available, but this is given here for the sake of comparison. And it is also being compared with a nearby place, nearby city, or suburban, which is providing this kind of value for the sake of comparison. So this is something that we are going to begin with in our next class, inshallah, which is the estimation of average solar radiation using a correlation. That would be it for today. And we'll see you, inshallah, in our next class next time.
Good, Doctor.